One of the reasons we try and doing these online courses, obviously, so we can have more people, but also if you can't make it to these sessions, they are being recorded at the moment, so you can look back at it. If there's things you're not sure about, if there's things you want to go over, you'll be able to do that as well. So that's the benefit of it. So we can have multiple people in here. So with the weeks that are coming up, and we might do a few more of these if the demand's there and if people want to do them, but what we're thinking about focusing on is chemistry, physics and biology, and that'll give us a nice sort of 3 weekly schedule of what we're going to be doing. So today we're going to focus on chemistry, and hopefully you can see that, and we're going to be looking at 6-mark questions. And the reason that we're going to be looking at 6-mark questions is because obviously these are the biggest point allocations in exams, and so therefore it's the areas where you can make the most gain. And also, if you can answer a 6-mark question about a topic, then generally you can answer a 1, 2, 3 or 4-mark question about it. So on the Google Classroom, I have put a sheet that looks like this one. You don't need to use it, you don't need to print it off. If you haven't got access to a printer, it's absolutely fine. Everything you need will be on the screen anyway, but if you're somebody that likes to write on it, see the questions as we go, we're going to have a look at them. So I don't really know how long this is going to take. We'll find out. It will improve as we go, but I've got 4 6-mark questions to look at. And each of them has got a key exam skill in it, as well as covering the content, and it'll be a bit of a reminder as we go through. So we're going to start off with the first question, which is this one. And what we're going to do is I'm going to give you a bit of time to have a think about it, and then we're going to join together and think about how we're going to answer that, making sure we get the top marks on these questions. So the first one is from the organic chemistry topic. It's all about fractional distillation. This is a really common long answer question in exams. It often comes up, so it's a really common topic as a longer question, and if it's not there as a longer question, it's generally there as a shorter question. So in this question, as you can see, it's talking about fractional distillation and the process of what fractional distillation is. And it gives you the table. And I like this question because it gives you information in a slightly different way to how fractional distillation questions normally are. So it's a little bit of a challenge. So you can see there it's giving you the fractions, and it's giving you 6 different fractions. So 6 different parts, so bitumen, LPG, fuel oil, heating oil, petrol, and paraffin. And it also gives you their boiling temperatures in degrees Celsius. And you can see that it's not in any order in terms of, well, actually looking at they are they? Alphabetical. But anyway, it's not in any order according to the boiling temperatures. So that's giving you something to think about. And so the question at the bottom is, list the fractions in the positions from top to bottom that they exit the fractionating column, and explain how fractional distillation separates crude oil into fractions. Now, with 6-mark questions, the biggest key to getting the full 6 marks in the questions is realising that in science, nearly every 6-mark question has 2 parts. Again, there's 2 things that you need to do. And often they're in the format of 3 marks and 3 marks, giving you the 6. But sometimes it might be 4 and 2, or very, very rarely 5 and 1. But there's always 2 parts to do. And this one's a bit more obvious. So the 2 parts are to list the fractions in positions from top to bottom, how they come out of the fractionating column. And then secondly, explain how fractional distillation separates crude oil into fractions. So with this question, it's a 4-2 split. You're going to get 4 marks for explaining how it separates it into fractions, and then you're going to get 2 marks for listing the fractions in position from top to bottom that they exit the fractionating column. So what I want you to do, I'm going to leave that on the screen. Hopefully it's big enough for you to see. If it's not big enough and you're not sure what to do, if you go over my screen on Google Classrooms with your mouse, and there's a little pin symbol. If you pin the symbol, it makes my screen bigger. So if you haven't done that before, I know lots of people here from my class, so you probably know what I'm talking about. If not, that should make it bigger and you can see it. So what I want you to do is to spend maybe just 3-4 minutes making some bullet points of how you'd answer that question. And then what we're going to do, we'll come back together and we'll think about how we're going to make sure we get those 6 marks. If you're really not confident on fractional distillation, then I want you to see if you can put them into an order. Think about what order they would go into. Not necessarily in the order in the fractionating column, but into some sort of order. So I'm going to say 3 minutes. That'll take us until 13 minutes past, and then we'll have a look at the answers to those questions. Okay, 3 minutes, over to you. Okay, so 3 minutes does shoot by, so let's have a look at how we're going to answer this question as we're going through, and I'm going to think about those key points. Hopefully this will also serve as a reminder of fractional distillation and how it works. So in a second I will put these points up on the screen as well, and as I said, we're recording this so you can view them later as well, so you don't have to rapidly write everything down. So the first point that happens is that the crude oil comes in. So the crude oil is a mixture of all of those different fractions. So all of those bits are in the crude oil. And then the first thing that happens to it when it's in the fractional column is that it gets heated. Okay, so the crude oil is then heated. There's fuel being burned at the bottom that's going to heat it up. Now what happens to that crude oil if it gets heated? This is where you're going to have to do some work in the chat. What happens to that crude oil when it gets heated? Spot on, excellent. Okay, it evaporates. Okay, so the crude oil heats up, it vaporizes, and it evaporates. So it state changes from a liquid to a gas. And as it does so, it rises up the column. Now what do you think the temperature is going to be like at the bottom of the column compared to the top? Excellent. Okay, so at this point it's going to be relatively hot at the bottom here because obviously it's close to the fire, it's close to the source of energy, and at the top it's going to be relatively cold. Okay, I'm just saying relatively cold because obviously it'd still be quite warm, but compared to the bottom it's cold and it's cooler. So as these fractions start to rise, they get hot. As they start to rise up here, they start to cool down. And at a certain point, when they get to their boiling point, or you could think about it as their condensing point, as they cool down, they're going to turn from a gas into a liquid. Fantastic. Okay, so they're going to turn into a liquid. So they're going to state change. And when they turn into a liquid, that's the point at which they are removed from the fractionating column. So they turn into a gas, they evaporate, and then as they rise, they cool, and they turn into a liquid. And so what you'll see is that they'll start to come out at different levels. Okay, so they'll start to come out at different levels. Those that have the lowest boiling points will come out at the top, and those with the highest boiling points would come out nearer to the bottom. So these would be our ones with our high boiling points, and down here, oops, sorry, wrong way around. Over here would be the ones with our low boiling points, and down here would be our ones with our high boiling points. And so there'll be a difference about those molecules. What would we say about the ones at the top? What would those molecules be like in terms of their sizes? Fantastic. These would be the small ones. Let's put it in. And these are much more likely to be gases when they're small. And down the bottom here, these are going to be the large ones. And they are more likely to come out as liquids and be quite thick and viscous liquids. So our small, simple molecules at the top there, and our large liquids molecules at the bottom. And we call this fractional distillation because each of these sections that come off we refer to as fractions, and that's where that number comes from. So going back to how we would write that, that's the information that we would want to get across. So our method we'd say is that the crude oil is heated, that the column has a temperature gradient, it's hot at the top and it's cold at the bottom. The vapours therefore rise, and as they do so they cool, and they condense when they reach their boiling point. So therefore the gases we collect at the top, things like LPG and the other gases, and the larger molecules like the bitumen exit from the bottom. So that's how we're going to pick up those marks. Okay, and if we wrote that, we're going to get ourselves around about 4 marks. Okay, that's probably the most we'll get on that question. So then where do we pick up the other 2 marks? So the other marks come from the order and trying to work out in which order they come. Now in the question it tells us to list the fractions in the position from the top to the bottom that they exit the fractionating column. So here we're just going to use the boiling temperature in degrees Celsius. So let's see how well we've done in the chat. Who can tell me what would come out at the top? Excellent, LPG, fantastic. And then let's see if we can get the next ones down. So we're going to be doing them in order. So what would come next after LPG? Excellent, it would be petrol because that's 40 to 200. So you can see how they're moving. After petrol, excellent, we know the pattern now, so we're going from 200 to 250 will be paraffin. After paraffin, heating oil. From heating oil, the penultimate one will be fuel oil. And then finally the last one would be bitumen. Excellent. And then if we include that in our question, that's going to get us the 6 marks. Okay, so that's how we answer those questions. So coming back to that question, we've hit both of the points. Okay, we've explained how the fractional distillation separates the crude oil into fractions, and that's a really common question, so make sure you're really clear on that. Okay, that's the knowledge to take away. And then the application part of the question was taking the information from the table and then putting it into order. And doing both of those things will get us our 6 marks successfully. So that is our first question done in terms of making sure we're getting those 6 marks. So let's have a look at our next question. So again, this is a really common exam question, and I've tried to choose things that are really common so they come up a lot. And this one's talking about life cycle assessments. And in the spec, it specifically mentions plastic and paper bags. Now that doesn't mean that you'll always get plastic and paper bags, but it does come up quite frequently. And it also means they're expecting you to have a bit of knowledge about it. Often with these questions, they'll give you a table of information. So you can see that we've got a table of information there when we're trying to choose which one is better. So this question's all about which is better, plastic bags or paper bags. And there's the question a bit bigger for you. So bags can be made from plastic or paper. You need to evaluate the use of these materials for making bags. You should use your own knowledge and use features of the life cycle assessments. So where I told you questions are always divided up, this one that's divided up into 4 parts. Okay, it's a bit of a strange one. It wants you to talk about the features of the life cycle assessments. So a life cycle assessment is, well, I don't want to give too much away, but a life cycle assessment is looking at the environmental impacts of a product for the entirety of its life cycle. And there are 4 parts to a life cycle assessment, and they are the key parts to know to answer this question successfully. So does anyone think that they can tell me what are the key parts of a life cycle assessment? So I'm going to have a quick look in the chat. What are the key parts? Excellent. So where the raw material comes from is definitely one of those key parts. So fantastic. So that's the first one. So we've got our product, our plastic or paper bag. The first part is the raw materials. Where do we actually get the stuff that it's made of from? Excellent. A lot of you are going for disposal, and that is another part. So that's the last part, how we get rid of it. So we've kind of got the birth and the death of the life cycle, where the materials come from to make it, and how we get rid of it at the end of its life. So what are the 2 stages in between? Spot on, manufacturing, okay, the packaging, the transport of it, that's definitely a key one. So that's the second one. So we've got the raw materials, and then how do we actually turn those raw materials into the product and what things are associated with the product. So the manufacturing and the packaging. And then what's that final step, the one that people sometimes forget before we dispose of the product? Ah, excellent. I can see a few of you have done it before. I missed it there. Spot on, it is the use. Okay, the use and the operation. What do we do with that product while we're actually using it? Some products have very short life cycles in that stage. You know, we use it once and throw it away. You know, maybe a crisp packet or something like that. Other things we might use multiple times. So when we're doing this question, when we're thinking about this question, how we're going to answer it, we want to think about answering it in terms of those 4 categories. So where we're comparing plastic bags and paper bags, we want to compare the raw materials that's used, the manufacturing and packaging, the use and operation, and the disposal. And realistically, we want to make a point about each, a comparative point, to help pick up those 6 marks. So again, like the last question, I'm going to give you a bit of time to think about it. Okay, so I'm going to give you a bit of time to think about the different parts and how you would get those marks. And then again, in a few minutes, we'll come back and we'll think about where those answers are. So I'm going to give you 4 minutes now, that'll take you until 4:28 to think about what you could put in those. And I'm going to put it back onto the table because that might help you with some of those parts. Okay, good luck, and I'll speak to you in 4 minutes. Okay, so that's 4 minutes of time. So let's have a quick look at some of the things that we might talk about. So firstly, with plastic bags and paper bags, we're talking about the raw materials. So what could you compare about the raw materials of plastic bags and paper bags in terms of their life cycle assessments? Let's see in the chat, anyone got any ideas? So definitely it's about sustainability, but let's give the detail then. So what's different about the raw materials for plastic bags and paper bags? Excellent. Okay, so spot on with those ideas. So it's all about the idea of finite resources. Okay, so going back to the table, and if I just flick back to the table here, you can tell it telling us that the raw materials for plastic bags are crude oil or natural gas, which we know are finite resources. Whereas paper bags are made from wood, and obviously wood is a renewable resource. We can grow new trees. So that's your comparative point between the two there. Crude oil to make the plastic is finite, whilst the trees that make the wood are renewable. So we've got a nice comparison point between what they're made of. We've used information from the table and we've started to make a comparative point. So that would be the start to picking up those marks. So let's move on to the next part, which is the manufacturing and packaging. So we're really thinking about the manufacturing here. You don't really have the packaging for plastic bags. So what's different about the manufacturing that we could use here? Good, so both of the ideas are, both your ideas there are picking up exactly what it is. So again, we're using the data from the table. Okay, so if I scroll back very quickly to the table here, you can see the mass of carbon dioxide being produced and the volume of fresh water. And in both cases, the paper bag is producing more CO2 and using more fresh water. Okay, so you can start to compare them in that sense. So to get the full marks, quite often, what you want to do is to make a comparative statement using numbers. So some of you might have noticed you could use the numbers. So for example, for the CO2 produced, it emits less greenhouse gases in manufacture. You could say it's half. If you look at the carbon dioxide production, it's half, 0.26 is half of 0.52. So it's often good to make those comparative statements. The volume of fresh water, I think, is 4.7 times less in a plastic bag. Okay, so you can see the differences between them. So we've kind of used all the information from the table now, and the question was asking us to also use our own knowledge. So that's where it's going to come in a bit more. Our own knowledge is going to come here into the use and the operation and the disposal. So what might be different about the use of plastic bags and paper bags? Good, so I can see lots of really good ideas going in the chat, mainly to do with the use. Paper bags tend to be single use, they're much more likely to get destroyed. Plastic bags can be used a lot more. So plastic bags can be used up to around about 50 times. The number you don't need to remember that number, the idea that they can be reused, whereas paper bags are much more likely to be break and be replaced, and that obviously has an impact on its life cycle. And then finally, we've got to think about the disposal and what might happen to them. And again, this is where your own knowledge is coming in. The information isn't in the table that you're given. So what might be different between plastic bags and paper bags? Excellent, I'm seeing lots of fantastic words. So the ideas of decomposition and biodegradability. So the idea that plastic takes a lot longer to decompose, or it might not, whereas paper bags are biodegradable. Again, we could think about the disposal, because it doesn't have to be thrown away. Plastic bags maybe could be recycled or could be reused if we're trying to think of a positive, whereas the positive obviously for paper bags is that they're biodegradable, whereas plastic bags are not. And again there we're hitting all of those points, and the key to getting the 6 marks here is to know the parts of the life cycle assessment, to talk about raw materials, manufacturing, use and disposal. If you don't hit those 4 things, then you're not going to be picking up all of those 6 marks. So there we are, we're halfway through. We've got 6 mark questions. We're going to be moving on to question number 3, unless we've got any questions about that one there, as I did move on quite swiftly. No, good. Okay, so question number 3 is quite a wordy one here. So it's the sodium thiosulfate reaction. So sodium thiosulfate there, Na2S2O3, reacting with dilute hydrochloric acid. Now, you might remember this reaction. Unfortunately, we didn't undertake this practically in class due to the conditions. And when you did it, but you've probably seen a video of it. And if you haven't, I really recommend Malmesbury Science education videos. They're fantastic for going through this practical. But it's the one where you mix sodium thiosulfate with the acid and it produces sulfur there in the products. And what can you tell me about sulfur if you see it in the products there? What's the important thing to note about it? Spot on, it's a solid. Okay, so if you look at the state symbols, you can see the S and then they've got the bracket S. It's a solid here. So this bit here. So because of that, it's what we call a precipitation reaction. So this reaction gets cloudier. Okay, it gets cloudy. It goes from being clear to being cloudy. And therefore you can try to measure how fast the reaction is taking place by measuring how quick it takes to become cloudy. So it's a really common reaction. It's one of the RPAs. Again, check out the RPA booklets on my website if you want to learn more about it. But it says a student wants to investigate the changing temperature on the rate of this reaction, and you need to devise a method that the student could use to find out how the time taken for the precipitate sulfur becomes visible. To become visible changes with temperature. Give a reason for each step of the method. So like I said, every 6 mark question, every single 6 mark question has 2 parts to it. Every 6 mark question has 2 parts to it. So the first part of this one is obviously to devise the method. What's the second part of this question? What's the second thing that you need to do? Excellent. Give a reason for each step. So this is one of those really common 3 mark questions. 3 marks for the method, 3 marks for giving a reason for each step of the method. So I'm going to talk you through the method, and what I want you to do is to tell me what the point is, what the reason is for each of those points. So let's go back here. So we'll work through this one together. It might be a little bit quicker. So the first thing you want to do is use a pipette to measure out 50 centimeters cubed of your heated sodium thiosulfate solution into a conical flask. Okay, so what's the key thing I'm doing here, and what's the reason why I'm doing it? Excellent. I'm using a pipette for accuracy. Okay, so it's about choosing the correct piece of equipment. That's what they're looking for here. So the pipette ensures your accuracy of measurements. Okay, a pipette's better than using I don't know, a beaker, for example, to measure out 50 cubic centimeters. Okay, so it's making sure. You could also talk about, consistency to make sure your results are comparable. That would also be important as well, because when you do it with another temperature, you would also need 50 centimeters cubed. So to ensure that you've got comparable results would also be a perfectly valid point. So once I've measured out the sodium thiosulfate, I'm going to place the conical flask onto a black X drawn on a white piece of paper. So what's the reason? Why am I putting it onto a black X drawn on a white piece of paper? Excellent. All about visibility. Yeah, so we want to make it as clear as possible to see that X. Okay, so the white background with the black cross ensures that the cross is clearly visible. Fantastic. So our next step, we're then going to use a different pipette to measure 20 centimeters cubed of hydrochloric acid into the flask, and we're going to start the timer. So what could you say here about reasons? There might be a couple of things to think about. Good, so a lot of people spotting this as a different pipette. Obviously, if you're measuring out a different chemical, a different solution, therefore you don't want them to mix up, you don't want the reaction to occur before you've started mixing them. So using a different pipette will solve that problem. Fantastic. And then obviously starting the timer only after you've added the acid into the flask, so that you're not missing that time. You start the timer and then you start measuring it out. Obviously you're not going to start the reaction when the time occurs. So there's a couple of things that you could talk about there. And you can see how important it is to make your method really clear, to make sure you're drawing out those reasons, to give yourself those marks. Okay, then you're going to stop the timer when the cross is no longer visible and record your results. So why are we doing this step? Exactly, so we can find the end point. Yeah, we want to make sure when the reaction is at the same point, again, so our results are comparable. So we're doing that to judge the end point at the same point, yeah, when the cross is no longer visible to our eyes. And often in these questions, they like to talk about improvements that you could do here. Yeah, so there's that past paper question about using a light sensor. So that would be something you could talk about that we were doing today. And then the final step, you just repeat with a different temperature of sodium thiosulfate. And again, that allows you to then compare the results. I mean, there is extra detail that we could put in there. We could talk about how we might get the different temperatures of sodium thiosulfate. So using water baths and things like that. But we're thinking 3 marks. We've definitely got 3 marks. We've got more than enough on the method, and we've got more than enough reasons. So we're confident that that shows the practical, and then that we've got our 6 marks clearly drawn out. So again, hopefully we're feeling a bit more confident in terms of these 6 mark questions, and we're starting to see how we can build them up. Now, yes, it's important that you know the method for that practical, but it's much more important that you know how to do the method for lots of those practicals and how to answer those questions. Again, Mr. Taylor always recommends, okay, bullet points are really useful ways to lay out method questions. Yeah, you want it step by step. Bullet points really going to help you with that. Okay, let's move on to the final question that we're going to be looking at today. So we're going to compare these 2 chemicals on the side. So we've got alkanes and we've got alkenes. So which one of the 2 is the one on the left or the right? Which one of those is the alkane, and how do you know? Excellent. So the alkane is there on the left, the one with the single bonds, and on the right is the alkene with the double bonds. So in this question, it's quite an open question. It wants you to compare the alkanes with the alkenes, and you should refer to 2 things: their structure and bonding, and their reactions. Okay, so again, I'm going to give you a bit of time to think about it. And again, you can see quite clearly in this question 2 parts. The 2 parts are the structure and bonding, 3 marks, and their reactions, 3 marks. If you're doing the separate science course, you'll probably have a little bit more to say about their reactions. If you're doing the combined course, you might go with a 4-2 split, 4 marks on the structure and bonding, and 2 marks on the reactions, because you don't do as much of that in that course. Okay, so I'm going to again leave you with that there, and I'm going to give you 4 minutes, and then we'll see what we can come up with together. Okay, so let's see how we're getting on with those. So when we're comparing, we obviously want to think about similarities and differences, and we think about structure and bonding, and then their reactions. So let's start off with similarities. What are the similarities between alkanes and alkenes in terms of their structure and bonding? Good, so they're both hydrocarbons. Okay, so they're both made of hydrogen and carbon atoms only. So that would be a nice similarity. You know, got any other similarities between them? Maybe think about what type of bond there would be between hydrogen and carbon. Excellent, so they're both made of covalent bonds. Spot on. So they're both hydrocarbons made of hydrogen and carbon only. They've both got covalent bonds. Fantastic. So what about the differences? What differences could we come up with between them? Excellent, I can see loads of different examples, so let's go over to here. I like the use of those arrows as well, not seen that. So, yeah, alkanes contain the single bonds, or only single bonds, whereas alkenes also contain double carbon bonds. Okay, so that would definitely be a difference between them. You could talk about their general formulas. Alkanes obviously have the formula CnH2n+2, alkenes have the formula CnH2n. So yeah, that key point about being saturated or unsaturated. Fantastic. So what about the reactions? What's similar about their reactions? And this is maybe where it gets a bit trickier. So you can see how this question is moving up to that higher level, struggling a bit with the similarity. Excellent, so they combust in similar ways. That's a really key thing. They're both hydrocarbons, so they combust in similar ways. So if they undergo complete combustion, what would they produce? So they produce carbon dioxide, and they could also produce, if we're talking about complete combustion, so I can see some people putting carbon monoxide and soot, but if we're talking about complete combustion, they can produce water and carbon dioxide. They both can also do incomplete combustion, and that's where they'd also produce carbon monoxide and carbon as well as water. So just be careful. So if it's complete combustion, you'll produce carbon dioxide fully. If there's incomplete combustion, you'll also produce carbon monoxide and carbon. And you're right, alkenes are much more likely to undergo incomplete combustion. They produce smokier or sootier products when they're burnt. So there's the similarities. They both combust, and when they react with oxygen completely, they produce water and carbon dioxide, and an incomplete carbon monoxide and carbon. What about differences in their reactions? Definitely. So alkenes are more reactive. Yeah, they can react with other things, so hydrogen, water, and halogens, and also go on to make the polymers. So alkenes are much more reactive than alkanes. And I said this is that separate topic part. So if you're doing the combined, you'll probably know less about that second box there. But you will know the first one. So remember the test between them, the bromine water test. Obviously alkenes turn bromine water colourless, whereas alkanes don't. So you'd be able to pick up the mark because you'd know those points. And as you can see there, I've got 8 marking points. You'd only need 6 to be able to get yourself those 4 marks on the questions. I'm just really making sure we're picking up those marks and looking for those different alternatives. And so again, you can see that I'm really making sure I'm picking the key parts of that question. It's a compare question, so I've got similarities and I've got differences, because that's what comparing is about, what's the same and what's different. And I've hit the 2 things they've asked for, structure and bonding and reactions. And if as long as I get 6 of those, 3 from the top, 3 from the bottom, then I'm going to give myself a well-rounded answer and pick up those 6 marks. So there we go. That's 6 mark questions in chemistry, how to pick up those 6 marks on those trickier questions. Hopefully that's been really useful and it hasn't been too difficult doing it virtually. I'll see quite a few of you tomorrow in lesson, so I'll ask for some feedback. If you could let me know what we could do to improve it, how the time works for you, the resources. Obviously, if you're in my class, I gave them out. If they worked online, any feedback would be fantastic. Whether you prefer it online, the fact that it could be later and that you're at home doing it, or we could swap around. But there we go. So hopefully that helps. Some really key topics there, things that commonly come up. So we've got an RPA question on the sodium thiosulfate, we've got a life cycle question, we've got a fractional distillation question, and we've got a compare question. So some really different types, but also some really key 6 mark questions. So as I said, hopefully that helped, and that's where we're going to leave it today. If anyone has any other questions about anything, you're perfectly welcome to put them in the chat. Otherwise, have a lovely evening and goodbye. Happy sciencing.